Hi, and welcome to the second video on the series about enumerative combinatorics. I've actually decided now from this video forwards to write in real time so that we can follow along better than if I just read off of what I've already written. So in this, we'll be looking at some results that actually tie into some that follow from what we covered previously. And what we've done previously, as I can just scroll up here since I'm on the same set of notes, we looked at the number of subsets of a set with a certain cardinality, up here just being if S is of n variables, an n set, then it has 2 to the n subsets. We defined this choosing over here, S choose k, to be the set of all k subsets, and we showed that if n is the cardinality of S, that this binomial coefficient, so to speak, is of this form. And then after that, we looked at a generating function approach to regarding these binomial coefficients, a powerful tool, by looking at x1 through xn as independent indeterminates and then taking the product and then the sum this way. We looked at a more general result where over a collection of finite sets with an unspecified function of n being the number of sets with n elements, and then this formula here which followed. And in this video, we're going to be going over something that's very similar to, very connected rather, to the subsets of a set, and that is compositions of a non-negative integer, or rather a natural number, as we can say. So compositions of n in this boldface n, just the natural numbers. We can think of a composition as an ordered sum of integers. And there are certain definitions in which, by permuting the elements in the sum, then you get the same thing. But a composition, the order does in fact matter. So we can write it as an ordered sum of integers, a sequence alpha equals alpha 1 through alpha k. If this composition has k elements, we call it a k composition. And we take this sum over here over ai, which equals n, because we want this composition to be of things that add up to n, right? So we'll just look at an example for n very small, because there are a huge number of compositions for larger numbers. So we take compositions of 4. Of n equals 4. There's the simplest one, which is 1 plus 1 plus 1 plus 1. I shouldn't say simplest because there's actually just 4 by itself, but rather it's the most molecular one. And then we can group these 1 plus 1s, and we can say 2 plus 1 plus 1. Rearrange these 1 plus 2 plus 1, 1 plus 1 plus 2, 3 plus 1, and then 1 plus 3. Switching these around, then you have 2 plus 2, and you have 4. You can check that there's no more, but there are 8 compositions of 4. Let's go a little bit further, and we want to detail maybe what are the kinds of compositions of 4. So we have one 4 composition, which is just 1 plus 1 plus 1 plus 1. More generally, we can notice actually that when it comes to if n is an integer and we have n compositions of n, there's uniquely 1, because there's 1 plus 1 plus 1 n times, so on. So we have 4 compositions, then we go decreasing, so we have these three compositions. We have 2 compositions. and we have 1 for composition. And similarly to this first case, we know that, of course, if we're looking at any one composition of n, there are, there's only one way to express it, it's just n. Actually, why am I writing the of here? Okay, so we have 1 4 composition, 3 3 compositions, 3 2 compositions, 1 1 composition, which consists the 8. Okay. Let if A1 through AK is a K composition of n, I'll just write like K comp now going forwards because it's less letters, of n, define a K minus 1 subset as follows. S alpha of 1 through n minus 1. And this is actually a good time to introduce a bit of notation here. We denote the set of indices, or the set of natural numbers up till, in this case, n minus 1. Just writing bracket n minus 1, nice shorthand. And the sentence doesn't end there, so we want to define it by S alpha equals A1 plus A2, so on till A1 plus AK minus 1. Then we have a map from alpha to S alpha, right? We have a map from this K tuple here to this partition set, rather, here, between all K compositions of n just bijection. K compositions of n with K minus 1 subsets of n minus 1, or n minus 1 elements. From this, we can actually define a very useful explicit formula. We have n minus 1 choose K minus 1 K compositions of n, right? Because of this bijection above. And we have 2 to the n minus 1 compositions of any positive n strictly. Okay, and this follows from 2 to the n being the cardinality of the subsets, the set of subsets of anything with n indices or elements. Okay, so now we have that map alpha to S alpha. Since it's a bijection, there's an inverse map, an inverse bijection. From S alpha into alpha. And this is represented in a very convenient geometric way. We want to draw n dots, and we want to draw k compartments, let's say. So k, first I'll just draw out an example, and then I will explain why this actually represents this bijection here. Let me do this in a different color now. So if we have this dot, this bar, these two dots, this is sometimes called the stars and bars method. Let's do 3 here, and then let's do 2 more right after it. This represents the 6 composition, since we have 1, 2, 3, 4, 5, 6 compartments. 1, 2, 1, 1, 3, 2, which is a 6 composition of the total number of dots, which is 1 plus 2 plus 1 plus 1 plus 3 plus 2, which is seen to be 10. And the n-1 and the k-1 come in here because to divide k compartments, we need k-1 vertical bars, right? So we have 5 bars here to divide things into 6 spaces. This is a very useful idea. And between the n dots here, these 10 dots, there are n-1 spaces that separate them when you draw them in this linear ordering like that. So this is the n-1 choose k-1, and now we're sending that this bijection from S alpha here to alpha. So this is a 6 composition of 10. I hope this example helps. Now we're going to turn our attention to another problem that's very much related to compositions. It works with it. It's a slight extension to this. So how many solutions to actually, let me just write nk, not to be confused with the one that is above from the previous part, x1 plus x2 plus xn, sorry, actually let me use xk equals n in non-negative integers. Okay, so we want to solve this this Diophantine equation, so to speak, of k indeterminates on the left-hand side, and then some number n, which is a very general type of equation, really. So this is called a weak composition, or a weak k composition. And it's called a weak k composition due to the non-negative instead of strictly positive. So if we put y1 y sub I equals x sub I plus 1, we have this new thing y sub I for each corresponding xi in the sum here. Then nk enumerates solutions to, we're transforming the sum up here. Now we have y1 minus 1, y2 minus 1, and then yk minus 1. And these number of minus 1s are going to be, there's k of them. So then adding that to the right-hand side, we have y1 plus y2 plus y sub k, which is equal to n plus k now, right? So this is the number of k compositions, actually, of number of k compositions of n plus k. We saw above by this formula here, to find the number of k compositions of n, we just have n minus 1 choose k minus 1. Now transforming a little bit here, which is given by n plus k minus 1. We have this, the thing we're taking compositions of, and then the number of compositions we have here, which is k minus 1, which is a really, really nice formula to have. Okay, and now we have another sort of, I don't want to say generalization, but a different kind of problem related to that one. So variant. Solutions to the equation x1 plus until x sub k less than n in non-negative integers, or natural numbers. Now, the distinction is that now we're taking less than or equal to instead of equal to, and we use a similar technique to the previous problem here. This introduction of this new variable y is a slack variable. We call it a slack variable because it's sort of giving this room to the equation by introducing this new concept and then working around it, this new variable. So introduce equivalent. We want to find x1 plus until xk plus y, which is strictly equal to n. It's covering this discrepancy that makes it less than or equal to, and y ranges from 0 to whatever it goes up to, right? So now we have the number of solutions to this equation as we saw above. So the number n is going to be nk plus 1 now. It's going to be a weak k plus 1 composition of n. So there's k plus 1 here, and because we have 1 through xk, and now we have this additional y, which we can treat as sort of xk plus 1 even, because it's a slack variable. So now the number of solutions is going to be n k plus 1, which equals, sort of more complicated now, n plus, what will it be? K plus 1 minus 1, and then we take k, because we have k plus 1, and then we take minus 1, so those cancel. And conveniently enough, n plus k, because these ones cancel, choose k. Cool. So we have this formula here. Now we want to get into this interesting theory called that of multisets. And I will do this in a following video because it's a huge theory, it's extremely important, and it relates to these prior concepts. So I will see you in the next video, and thank you for watching.